everyone. Today we're talking about empirical formula. Empirical formula is a really important section of the organic chemistry topic and a way to get great marks in WACE exams. Last year in 2017, the WACE had a question on empirical formula that was worth 17 marks, which is obviously quite significant. So if you can follow the procedure and absolutely nail these, then you're going to maximise your score, which is what this is all about. So let's have a look at a simple example and then we'll follow up with a more difficult example of a Year 12 level. Okay, so here's the first example. We're looking at ethylene glycol. Ethylene glycol, they give us the sample mass. Now that is required in all empirical formula questions. And they've also given us the mass of carbon and the mass of hydrogen in this particular sample. Those two things are really important. This one's also got a bolt-on, which asks us for the molecular formula. To do that, we're going to need the molecular mass. And that must be given to you for you to be able to do these types of questions. Okay, so the first thing we need to do is to figure out what is the oxygen in this sample. That's the remainder in that first paragraph. Okay, so to do that, it's a fairly simple subtraction. Mass of oxygen is the mass of the compound that we've got, minus the mass of carbon, plus the mass of hydrogen. So the mass of the sample was 9.320 grams, and we take the mass of carbon and hydrogen from that, and we now have our mass of oxygen. So we have the sample mass in total. We don't really need that anymore. What we've got now is the carbon, the hydrogen, and the oxygen. They're the things we need to use. So what do? We make ourselves a simple table. This is one of the times where full working isn't really required. In every other calculation in chemistry, I need you to show full working with all formulas, all known quantities. Empirical formula, you can get away with this table format. So we write the mass of each in grams for carbon, hydrogen, and oxygen. We then need to determine the number of moles of each by determining by each substance's atomic mass, and we get a mole number for each of those substances, which is written in light blue there. We then take the smallest one. As you can see, carbon and oxygen are the same in this case. That's not always going to be like that, but in this case, the smallest one is 0.3003. So we divide each number of moles by that smallest number, and we get a simple whole number ratio. So the empirical formula for this substance is CH3O. Now we need to get the molecular formula. To get the molecular formula, we calculate the empirical formula weight, EFW. So we've got 1 carbon, 3 hydrogens, and 1 oxygen. Put those together, and we end up with 31.03 grams per mole. We then need to work out the molecular formula from the molecular formula weight, which is given to us in the question, which is 62.07 grams per mole. The molecular formula is always the molecular formula weight divided by the empirical formula weight times the empirical formula. We should get a whole number or close to. Now these are experimental results, so we're not always going to get perfect whole numbers, but we should get something quite close. If we do 62.07 divided by 31.03, we get 2. 2 times CH3O, that's the molecular formula of our substance, C2H6O2. Question answered. Now that's a very simplistic one. That's not something you're going to get in a Year 12 exam, but it gives you a bit of an idea about how to start. Now, what's more likely to encounter in an exam is actually a combustion reaction. This is where an organic substance is burnt in air to give its oxides. Now, if the substance only contains hydrogen and carbon, your oxides are going to be CO2 and water. Sometimes your organic substance might have other things in it, like sulfur, silicon perhaps, nitrogen, and that means we're going to get their oxides as well. So nitrogen dioxide, sulfur dioxide, silicon dioxide, they are all possibilities, especially at the Year 12 level, just to add that extra bit of complexity. Now we're burning in air, which means the oxygen is in excess. So you can never work out the oxygen directly because that's always going to be the excess, and that's the trick. So combustion is a process by which something is burnt in air to form an oxide. Most calculations you have to do involve the combustion of carbon, hydrogen, oxygen compounds. So for example, now the x, y, and z in that equation, they're just some numbers that could be for any number of carbons or hydrogens and oxygens. What you must remember is all the carbon in the CO2 comes from the compound. All of the hydrogen in the water has come from the compound. And what you do to get the oxygen, you can work out by subtraction. So here's an example. 3 grams of a compound was burnt completely in air. The sample is known to contain only carbon, hydrogen, and oxygen, which is great. Products form a carbon dioxide, 3.46 grams, and your water, 1.42 grams. Determine the empirical formula of the compound. That's the first part. The second part is the molecular formula determination, and they must give you the molecular formula weight, in this case 152 grams per mole. This is a general equation. It's used just to help us to calculate. It's not used for anything else. Okay, so first of all, we've got to work out the number of moles of carbon. Now that is equal to the number of moles of CO2 because it's a 1-to-1 ratio. That's really important. So we write our known quantities down the side. Number of moles is mass on molecular mass. There's our number of moles of carbon, and therefore our number of moles of from our number of moles of CO2. A number of moles of hydrogen. Now this is the key step. A lot of people get this wrong. It's 2 times the number of moles of water because there's 2 hydrogen atoms in every water molecule. So we known quantities down the side, mass on molecular mass, there's our number of moles of water. We've got to times it by 2 to get our number of moles of hydrogen, as so. Now oxygen we can work out by subtraction. First of all, we work out the mass of carbon by doing the number of moles of carbon times the molecular mass, so that's 0.943. Do the same thing for hydrogen to work out its actual physical mass and add the two together. Now the sample only contained carbon, hydrogen, oxygen, so we get the oxygen from the sample mass minus carbon minus hydrogen. And we do that as shown in the bottom, which is 3 minus 1.1009, 1.899 grams. So that's all done. We then work out the number of moles of oxygen by simply dividing by its atomic mass. So we go back to our table, same as we did before. Now because we've already worked out the moles, we don't need to write the mass in, we can go straight to moles. Moles are always important in chemistry. That's the only quantity we can compare. So we write down our carbon moles, our hydrogen moles, oxygen moles, divide by the smallest, which you can see is the carbon. We divide by carbon for each one of those, and we get a simple number ratio of 1 to 2 to 1.51. Now because it's 1.51, that's half 1.5 ratio. We can't put that into a chemical formula. There's no such thing as C1H2O 1.51. What we can do is we can multiply everything by a coefficient to get it to a whole number. So C2H4O3, and that evens out. Now, usually you want to times by 2 or 3 or 4. If you start timesing by anything more than that, you're going to get some strange results. Most of our numbers will be a little off. They're not whole because they're experimental results, so there always has a little bit of error. But what we want is a simple number ratio between each ones, and this means that the empirical formula is C2H4O3 in this case. That molecular formula now. Molecular formula weight is 152 grams per mole. That was given to us in the question. We work out the empirical formula weight by adding all the bits up in the empirical formula. So carbon, 2 of those, hydrogen, 4 of those, oxygen, 3 of those, and we end up with 76. To get the molecular formula, we do the molecular formula weight, 152, over 76, times the empirical formula. So 152 over 76, again, 2 times C2H4O3, there is our molecular formula. So we've figured out the empirical formula and the molecular formula weight. That is a basic empirical formula question, and hopefully you'll be able to do those and get them 100% right, and good luck.